most missed question. I can easily see why. So, measurements of young children, wherever, found the least squares regression line. Y is the height, X is the arm span. Suppose that a child with an arm span of 120 and 18 is added to the sample. What effect will this addition have on the correlation and the slope? So what I would do is plug in 120 into the arm span and find the Y value, okay? And I think you'll find out, I don't know, I don't want to guess. My guess is the Y value is 118. But whatever that is, if it's 118, it's got to, correlation will increase and the slope will stay the same. If it's higher than that, then the correlation will probably decrease. You want to have stay the same or increase. So my guess is that point has to be right on that line. Hi.
Sorry, I'm really out of it. I went to my work keys.
You went to work keys?
Yeah.
Already?
I know.
And zero?
And I'm going to type 0A.
This one you'll see again, I think. Which of the following is not a characteristic of the least squares regression line? The slope is always between -1 and 1. That should be like an automatic answer. The slope can be any value, right? Slope can be anything. The least squares regression line will go through X bar, Y bar. It will. The least squares regression line will go through X bar, Y bar. The least squares regression line minimizes the sum of the square of the residuals. That's what the LSRL means. The slope of the least squares regression line will always have the same sign as the correlation, and that is a true statement. And then the least squares regression line is not resistant to outliers, and it is. If you have an outlier on it, it's going to change it. Okay. Just a couple of things we want to make sure we go over. Our plan today is to go over 3.3. It will not take very long at all to go over this lesson. When we get done with this, we'll talk about what we got to go going for the next couple of days. And we'll have to slide out here a little early so that we can test. And y'all can get where you got to get to and all that, because today is such a wonderful day. As every day is when you don't show up to class on time. Nah, what's missing on your notebook? I know. So just watch, pay attention. This is like very minute. In fact, it's so minute in AP Stats that next year they're throwing this section out.
Why didn't they do it this year?
Y'all took it too late or too early. Yeah. There'll be one question or maybe two. I know there's one, but it's not a very big section. Okay, so transforming to achieve linearity. You guys learned in your mathematical career that sometimes not every data is linear, right? Sometimes it's exponential, sometimes it's quadratic, sometimes it's cubic. Who knows what it is, right? Most everything we've seen in our scatter plots have been linear, except we've seen some that are curved, okay? So we've looked at some scatter plots that are linear in nature. We've also seen some that appear nonlinear, okay? What do we do if data is not linear? Well, in other classes, you guys found a regression for that particular line. In AP Stats, what we do is we transform the data. We do something to either the X variables or the Y or both to straighten it up. So we make everything linear in AP Stats. So we just do something to it, okay? When data is not linear, we're going to transform one or both variables to achieve that linear line, okay? Now, used to, we would spend, I don't know how long in class trying to achieve linear lines. And what we found out is somebody might take the square root of something, might take the square root of X, and somebody might square the Y. And it did the same thing. And so because there's so much you can do to one or both variables, we're lucky in the fact that we don't actually have to do it. Okay? We don't have to do it. We need to know two things. Either it has been done or that it needs to be done. It has been done or it needs to be done. I guess you need to know why. But why is because it wasn't linear. So it needs to be done because it wasn't linear, or it has been done because it wasn't linear. Fair enough? So, because there are so many different variations of transforming this data, we will not have to do this. You need to recognize that it has been done or that it needs to be done. And so how much of that you want to write down in your little notes, I don't think, like I said, I don't think there's much of anything that we need to write down other than you just kind of have to learn this a little bit, okay? Let's go over some examples. And this, I think this will make sense to you, and then you can write down whatever you want to. We can go back, whatever you need to. Imagine I have been put in charge of organizing a fishing tournament in which prizes will be given to the heaviest fish. You know that many of the fish caught during the tournament will be measured and released. You're also aware that using delicate scales to try to weigh a fish flopping around in a moving boat is going to not yield a very accurate result. It's going to be much easier to measure the length of the fish while in the boat. I need a way to convert the length of the fish to the weight of the fish. You contact a nearby marine research laboratory. It provides reference data, yada, yada, yada. Here's the data that they gave us, the length of the fish and the weight of the fish. Good enough? One of the first things we always want to do is what? Look at the scatter plot of the data. So I'm going to look at the scatter plot of the data. That tells me a scatter plot of the data. Immediately I realize what? It's not linear. It's curved. Okay? Immediately. I don't need anything else to realize that. So I need to do something to either the X or the Y or both to straighten that bad boy out. Good enough? So here's what they did. They see this is length cubed. You know what? Something has been done to one of the variables. And not only do you know that something has been done, you have cubed the X variable. That says Y. It's straighter. Good enough? So you need to recognize what? Something has been done or that it needs to be done. It needed to be done. It has been done. Okay? This says plain old length. Nothing was done to that, but then this one says cube root of weight. Something has been done. Good enough? Which one's better? Don't know. After we do that, if we're really into this, we want to know which one's better, we'll look at R, we'll look at S, and we'll look at R squared, and we'll look at the residual plot, and decide which one of those two is better. But again, guys, we don't have to do that. They're going to have one of these, or they're going to have two of these, and you're going to basically, and you'll see this in an example too, of which one's going to be better and which one's going to be not as good. Okay with that? We took the logarithm base 10 of the values for the both variables. Here are some. So this is a computerized print output. This is where they took the log of both variables this time. So here is the scatter plot, really straight, and there is the residual plot. Remember what we want the residual plot to be? Completely scattered, right? We don't want it to be curved. We don't want it to be curved. So if it's completely scattered, somewhat like this one is, we're better than it was. Is this better than the other two? Again, we don't have to decide that. Okay? There is no way that they're going to ask you which one's better between this one or the previous one. They're going to ask you which one's better between this one or this one. Okay with that? Like, it's going to be so obvious of which one's better. All right. Oh, here we go. Sorry. Also recognize the computerized print output. Notice it says log weight, log length. So you know that we've taken the log of both variables. Good enough? Beautiful. Here's the y-intercept. There's the slope. We still need the slope and the y-intercept. The difference is going to be like, instead of y hat, we're going to have log y hat equals negative 1 point whatever plus 3 point log x. Okay? Beautiful. Gordon Moore, one of the founders of Intel, predicted in '65 the number of transistors would double every 18 months. This is Moore's law. Yada, 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 yada. There's the scatter plot. Horrendous. No way I would want to try to find a line for that data because I wouldn't even be accurate at all. Click. Years since 1970. Natural log transistors. Quite a bit straighter. Still probably not the greatest in the world. It kind of has a little wavy to it, but it's a whole lot better than it was. Good enough? Beautiful. Putting it all together, which transformation should we choose? How is the braking distance of a car? Yada da 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 da. Models 2 and 3. Da 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 da. So we got their tire wear and their length. Beautiful. Here is the predicted. Now this is something I haven't mentioned. Normally we talk about the X variable down here. They're using the predicted variable, which is the Y hat. Okay, and it's okay to do that. So they use the predicted braking distance, which is Y hat, and then this is the residual plot. So this is not the scatter plot, this is a residual plot. And we can see what from the residual plot? Curve, which is bad. I don't want to say bad, but it's not linear. It's not linear, okay? And up here I can see braking distance and I can do tread depth, so what? I haven't done anything to either variable, okay? So we need to. Now I look at this one, predicted natural log. That's kind of hard to read. It says LN, natural log braking distance. And then that one says residual. And this one says natural log braking distance. And this one says natural log tread depth. One of the hardest things students recognize when they're doing these is which one's the X and which one's the Y. So again, you see predicted braking distance. That has to mean that that is the Y, because we're always predicting Y. Good? So the natural log braking distance, that's Y. Tread depth is the X. You can also see tread depth right here is X next to the constant, okay? So a little bit better, a little bit better. Here's another one. This one says the natural log of braking distance. This one did the natural log of braking distance, just tread depth. Still curved, right? So out of those three, which one do we like the best? The middle one, the second one. Okay with that? And so again, that's just things you need to recognize. Which one's the best and why? And it's because this set of data will not result in a linear model. The first set will not result in a linear model. The second set did better than the other two. Good? So, whenever you're asked to do something like this, the first thing we want to do is plot the scatter plot. We'll look at it to see if it looks linear. If it looks linear, then we find the least squares regression line for it. We look at R, we look at S, and we look at a residual plot. The residual plot is the best thing to tell us if it's linear or not. R doesn't tell us, S doesn't tell us. It helps us to decide on how accurate we're going to be. So if R is really high and S is really low, then we're still accurate. We still could be better. So the residual plot's the only thing that really tells us if it's linear or not. Find the equation of the least squares regression line if you decide it's linear. Then you construct a residual plot to notice any patterns. And then if you decide, we'll keep going. Find S, find R squared, find R, use all that stuff to predict. If we decide that the residual's not, we got to go back and transform the data. Good enough? Again, you don't have to transform it. You just need to recognize that it has been transformed or that it needs to be transformed. And then, of course, why. Good enough with all that? Just 2 questions on your test. I know there's one. There may only be one. It's not a free response. Okay, it's a multiple choice, and I'll give you a couple of them, and you'll see practice on your homework. Yippee, yippee, yo. What do I need to go back over so that you can write something down, or do you need to write anything down? Can I kind of see why the notes are like they are? Which way? Back, 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 back. Beautiful. Okay. This is my task for you guys. You have 3.3 homework. 3.3 homework. I think I took out everything that doesn't really fit well. I have opened on AP Classroom progress checks. I think there's 3, 2 multiple choice and 1 free response. Okay, those need to be done by next Tuesday. Next Tuesday. Oh, yes. Yeah. Friday's a B day. Okay. I'm going to give you a worksheet that needs to be done by Tuesday. At some point, we're going to do a Frappy. I got 2 more free response questions I'm going to hand out. So basically 3 Frappies. Okay with all that? Good. And then I'm going to post multiple choices again. What's today? Tuesday. Thursday, we're going to do reflections from chapter 2 test. Okay, so we're going to spend some time on that. I got a couple different things I want to look at as opposed to what we did the first time. First time was kind of a trial run. I learned from that. You learned from that. We'll do it better, even better than we did the first time. Y'all got some great stuff from you guys. Thanks. That's why I'm giving you the progress checks, and that's why we're doing a little bit more free responses, because I got a lot of great, I won't say great, but I got feedback on that. Whole lot better to do it now than it is at the end of the year when I try to do these things. So, and then Friday's another review day. That's going to be completely focusing on this test that you're going to take on Tuesday. Everybody okay with what's happening? Okay. Next Tuesday. We have 2 more classes, including today. So 3 classes, including today. Yay? Yay? Huh, man. So glad you could join us today. Knucklehead. Beautiful. Anybody else got a question about something? Okay. Do y'all get, you go get what you want on this? Yes?